Hey everyone, welcome back. Ready for another deep dive?
Always. What are we looking at today?
This one is really interesting. Well, it's gonna blow your mind, I think.
Oh, good. I like those. Lay it on me.
Okay, so we're diving into this conversation about fat in the brain.
Okay.
But not just, fat as in like energy storage. That's the usual thing, right?
Right, that's what we usually think about. Fat as fuel.
Exactly. But these folks, the ones we're hearing from today, they go way beyond that.
Okay, I'm intrigued. What else could brain fat be doing?
Okay, so buckle up. They're talking about the possibility of super fast signaling in the brain. Like really, really fast.
We were talking faster than a speeding neuron?
Even faster. They even bring up the idea of faster than light signaling.
Whoa, okay. Now that's getting into some pretty wild territory. Signaling faster than light. How's that even possible?
That's what we're going to unpack. But just a heads up, this is all pretty speculative stuff. We're talking about the edge of what we know about the brain and physics.
Got it. Speculative, but potentially mind-blowing. Let's dive in. All right, so the conversation starts with a pretty simple question. Why does the brain have so much fat in the first place? I mean, yeah, it's an energy source, but could there be more to it?
Right. There's got to be something else going on. The brain doesn't usually do things just for one reason.
Exactly. And that's where things get interesting. They start talking about how fat, because it's such a good insulator and also a good conductor in some way.
Right.
Well, it could be playing a key role in the brain's electromagnetic activity.
Ah, okay. So not just fuel, but like the wiring of the brain's electrical system.
You got it. They're suggesting that fat molecules might be acting like tiny antennas, helping neurons send and receive electromagnetic signals.
Tiny antennas in our brains. I love it.
Right. And they think this could be one of the reasons why the brain is so incredibly fast and efficient. Like it's using fat to create these super speedy communication pathways.
Okay, that makes sense. So it's not just about the energy itself, but about how efficiently that energy can be used for communication. Like comparing a sports car to a heavy truck, right? Both have energy potential, but the sports car is built for speed.
That's a great analogy, and that's kind of what they're getting at with Einstein's EMC too.
Wait, hold on. Einstein and brain fat, how does that fit in?
Well, they're not saying the brain is breaking the speed of light because of its mass or anything.
All right.
It's more like and they're saying fat allows the brain to tap into the energy potential of its mass in a much more efficient way.
Okay. So more about using the energy we've got in a really smart way.
Exactly. Now, here's another piece of the puzzle. It's not just fat. They also talk about the importance of water and oxygen.
Water and oxygen. I mean, yeah, those are essential for life, but how do they fit into this super fast signaling idea?
Well, each of them has unique properties that make them interact with electromagnetic fields in really interesting ways.
Okay, like what?
Well, water, it's a polar molecule, right? So it actually aligns itself with electromagnetic fields.
So like if you have a magnetic field, the water molecules line up with it.
Yeah, exactly. It's kind of like how iron filings arrange themselves around a magnet.
Okay, so water molecules are like tiny compasses following the brain's magnetic signals.
Perfect analogy. Now, oxygen's a little different. It's paramagnetic.
Paramagnetic. Refresh my memory on what that means.
It means it's actually attracted to magnetic fields. So imagine this. You've got these water molecules lining up, creating these pathways, and then you've got oxygen rushing in.
Drawn in by the same magnetic fields.
Yep. And they think this interplay between fat, water, and oxygen could be creating a system in the brain that's capable of signaling way faster than we ever imagined.
Okay, now we're talking. Fat is wiring, water are tiny compasses, oxygen rushing in. This is getting pretty wild.
It is, right. And that's just the beginning. We're going to dive into some even more mind-bending possibilities in the next part. Stay tuned.
Can't wait. All right, so last time we were talking about how fat, water, and oxygen might be working together to create these super fast signals in the brain.
Yeah, and I'm still kind of reeling from that. I mean, it's like the brain is this incredible electrical circuit we never even knew about.
Right. And the conversation we're looking at, it gets even wilder. They start talking about quantum stuff.
Quantum physics. What's that got to do with the brain?
Well, they bring up this idea called quantum coherence.
Okay, I've heard that term before, but I'm not sure I really understand it. What does it mean exactly?
So in the quantum world, things can be in multiple states at the same time.
Right, like Schrodinger's cat.
Exactly. Like
Yeah.
it's both alive and dead until you open the box. Quantum coherence is kind of like that, but on a larger scale. It's when a bunch of particles are all linked up in this weird fuzzy state where they're kind of doing multiple things at once.
Okay, I think I'm starting to get it. So are they saying that, like, neurons are in this quantum state?
Well, they're not exactly sure how it would work, but they're suggesting that maybe this coherence is happening inside these tiny structures called microtubules. They're these like little tubes inside neurons.
Huh. Microtubules. I vaguely remember those from biology class.
Right. And they think these microtubules might be the key to understanding how quantum effects could be happening in the brain.
Okay, so we've got quantum coherence happening in the brain, maybe. But how does that actually lead to faster than light signaling?
All right, so this is where it gets really mind-bending. In quantum mechanics, there's this thing called non-locality.
Non-locality. Another one of those terms that makes my head spin.
Yeah, it's a tough one. But basically, it means that two particles, even if they're really far apart, can be linked up in a way that they can influence each other instantly, like faster than the speed of light.
Whoa, wait a minute. Faster than the speed of light. Isn't that impossible?
Well, according to Einstein's theory of relativity,
Mm-hmm.
yeah, nothing can travel faster than light.
Right.
But here's the thing. What if the information isn't actually traveling? What if it's more like these particles are just connected in a way that we don't fully understand yet?
Okay, so it's not that the signal's breaking the speed limit. It's more like they're taking a shortcut through some weird quantum tunnel.
Exactly. And that's what they're suggesting might be happening in the brain. That these microtubules, through quantum coherence and non-locality, could be creating these instantaneous connections between different parts of the brain.
Okay, I'm going to be honest. This is a lot to take in, but I'm also really intrigued. I mean, if this is even remotely true, it would totally change the way we think about the brain.
Right. And it's not just quantum stuff they talk about. They also bring up this idea of resonance.
Resonance, like sound waves?
Kind of, but more like electromagnetic resonance. So think about a tuning fork.
Okay.
If you hit one tuning fork, it vibrates at a certain frequency. And if you have another tuning fork that's tuned to the same frequency, and you bring it close enough, the second one will start vibrating too.
Yeah, I've seen that before. Pretty cool.
Right. And they're saying that something similar might be happening in the brain, that different parts of the brain could be resonating with each other, creating these sort of synchronized patterns of activity.
So instead of just sending signals back and forth, it's like the brain is using resonance to create this whole orchestra of activity.
Exactly. And that brings us back to fat, water, and oxygen. Because their unique properties might be what allows the brain to create these resonant fields in the first place.
This is getting so complex. But it's also starting to make sense in a weird way. Like, all these different pieces fit together to create this amazingly fast and efficient system.
I know, right? It's like we're looking at a whole new level of complexity that we never even imagined before.
Okay, so we've been talking about quantum coherence, non-locality, resonance, all these mind-blowing ideas about how the brain might be working.
And I think it's safe to say, our minds are officially blown, right?
Definitely blown. Here's the big question. How do we actually know if any of this is true? Like, how do scientists even study these things, especially if they're happening so fast?
That's the challenge, isn't it? The brain, I mean, it's the most complex thing we know of. Billions of neurons all firing away. And now we're talking about processes that could be happening at, like, the quantum level.
It's like trying to study a lightning strike with a slow-motion camera. You just can't capture it.
Right. And the tools we've been using to study the brain, they're amazing, but they might not be fast enough to see what we're looking for.
So what are scientists doing about it? Are there new tools being developed?
Oh, yeah. There are researchers working on some really cutting-edge stuff, trying to develop technologies that can measure the brain's electromagnetic activity in much greater detail and at much faster speeds.
That's awesome. So maybe someday we'll actually be able to see these super fast signals, these quantum connections happening in real time.
I hope so. That would be incredible. But even if we can't see it directly, even if it stays theoretical for a while, just thinking about these possibilities, it changes our whole understanding of the brain.
Right. Like, it's not just a chemical computer anymore. It's this, I don't even know what to call it.
A quantum orchestra.
I like that. A quantum orchestra. And who knows what kind of music it's playing? What if these ideas about super fast signaling and quantum effects and resonance, what if they turn out to be true? What would that mean for neuroscience, for medicine, for, just our understanding of ourselves as humans?
That's the really exciting part, isn't it? The implications are huge. If we could understand these mechanisms, really understand them, we might be able to treat brain disorders in completely new ways. We might be able to enhance our cognitive abilities. Heck, we might even be able to create entirely new forms of technology based on these principles.
Whoa, Okay, now I'm getting chills. It's like we're on the verge of something really big, a whole new era of brain science.
Right, and not just brain science. It could change the way we think about consciousness,
Mhm.
about reality itself. I mean, if the brain can tap into quantum effects, who's to say what else it's capable of?
Wow. I think this deep dive has officially broken my brain in the best possible way.
Me too. But that's what it's all about, right? Pushing the boundaries of what we think we know, exploring the mysteries of the universe. And the biggest mystery of all might be right here, inside our own heads.
This has been an amazing deep dive. Thank you for taking this journey with us.
Absolutely. And keep those brains buzzing. Who knows what incredible discoveries are waiting just around the corner?